Continuing to talk about rotation, now we're looking at the resistance to rotation, the rotational analog to mass. So in our look at F net equals ma, we saw that the larger the mass, the harder it was to accelerate it. So if I have a refrigerator and I'm pushing it across the floor, if that refrigerator has stuff in it, more mass means that if I push with that same force, it's not going to accelerate as much. There's a connection here to rotation, as there have been many so far we've discovered. To get us there, we're going to look at a string, massless string, tied to a puck here, and you're going to give it an old kick. And when you kick it, it's going to, of course, travel in a circle, but just looking at this moment, when you kick it, we could look at the torque on that puck that's causing it to rotate, if this is our fixed point. So the torque is F times R times sine of theta. So sine of theta, well, that's 90 degrees, if that's a right angle, and so that's just 1. So FR. I'll look at F a little bit more and say that F is ma, because F is the only force applied to the puck in this direction. So I start with that. I know an expression for acceleration. That's angular acceleration times r. And I can now write this expression. M times angular acceleration times r, where this is my r from the distance from the axis of rotation to the point that is being rotated. Now, I can plug all that in for F, and I get this lovely expression, and simplified, I get this. This angular acceleration is the acceleration of this puck, and no matter what I have along this string, suppose I have 2 pucks here or 3 pucks here, they're all going to rotate with this angular acceleration. Now, this term here is dependent on the mass in the r, which is the distance that mass is away from the axis of rotation. This is what we call the moment of inertia. And the moment of inertia is the resistance of an object to change its motion, change its rotation, and that's in alpha, the angular acceleration. This is the rotational analog of mass for linear motion. So I is dependent on the axis, or how far it is from the axis of rotation, and it's dependent on the object's configuration. So consider that I have this blob here, and I'm getting this thing to rotate in that direction, and this is fixed, and this is a bird's eye view. I would have to look at every single piece of mass individually and consider how far away it is from the axis of rotation and add it all up to figure out an I for this specific object. And that involves calculus, and we don't really touch on that. So to get a true expression for the I of any object, you would need to add up the mass times the radius squared of each individual piece to get an I for that body. So we could get a number, maybe that I is, say, 0.23. And the units for I we could figure out are kilogram meter squared. And it would be different for, say, an object that looks something like this. Even if these two have the same masses, they have a different configuration, which causes a different I. So maybe this I is 0.7 kilogram meter squared. If we're just talking about a point mass, which we could assume this to be in our problem, then the moment of inertia is mr squared. Journey with me over here to the other board. I am hoping and praying that you guys are comfortable with F net equals MA. to solve most motion problems. The analogy to rotation is an equation for torque net. So adding up all the torques can give you an expression that you'll set equal to the mass equivalent, which is moment of inertia times angular acceleration. So here below I've listed out some common moments of inertia for different objects that you'll regularly see. You don't have to memorize this. Most of the time it'll be given, or it's going to be something that you would need to solve for. For instance, you would have a bunch of torques acting on an object, and you know the object's acceleration, its angular acceleration, so you could figure out, say, the moment of inertia of that object. So here I have 4 different common moments of inertia, and I asked which object will be easier to rotate. Well, if an object has a greater moment of inertia, that means that with the same torque, there's going to be a lower angular acceleration. So the largest I would be here. So this is, remember, this is the analogy to mass. So something with a larger mass would be harder to accelerate. Something with the highest I, oh, I got a rat climbing on me. Something with the largest I would be the hardest to accelerate. So I'm going to say my moment of inertia, object A. That's going to be the hardest to rotate. The easiest will be this down here, and I'm telling it by the coefficients. All of them involved in mr squared, but this is 1/2, and this over here is 1/12. So it's easiest to rotate a rod about the center, assuming that you have the same mass. I understand that all of these r's will be, could be a little bit different, but we're going to assume that they are roughly the same, and the coefficients are really what we are after here, if all of the masses are also the same. So the rod about the center, that's object C, will be easiest to rotate. Then object D, followed by object B, and then A. And if you apply a torque to a rod here, so I've got this rod, and I'm going to consider either turning it about the middle, so that's what the picture is showing, rod about the center, or rod about the end. Well, you should already have some idea in your mind about which one would be harder to accelerate, even without knowing the mathematics behind this. So if I generally give this the same force, I can accelerate my rod, something like that. And given the same force, this is a little bit harder to get moving because there's so much weight out there. And if this rod was even longer, I would have to apply even more force to start accelerating it. So I would say, which will cause the largest acceleration? Well, C. So this is moment of inertia. In this unit, we are going to be looking at applying torques to 2 torques to a pulley, figuring out the angular acceleration, and then ultimately trying to get an approximation for the moment of inertia of that pulley. You should be able to start thinking about how you would do that in order to feel comfortable doing it in class for a lab. All right, that's it for this time. I will see you soon.